triangle that I had you fill in, it's known as Pascal's triangle. This triangle, first off, what pattern did you use to fill it in? Addition. Those two add together gives me that one. Those two added together gives me that one. Those two added together gives me that one. Now with this, you also have to recognize that the outsides are ones. What other patterns are there? Nothing? We didn't recognize a single other pattern? Go for it.
So there's like second one in, like diagonally goes 1, 2, 3, 4, just adding by 1.
The second diagonal row, 1, 2, 3, 4, 5, 6, 7, etc. Both directions. It's another pattern. Put the phone away. Go for it.
The third one diagonally goes, like it adds 1 each time, so it's like 1, 3.
Plus 2, plus 3, plus 4, plus 5. Yep. Keeps increasing by 1 how much it's adding. Any others you noticed? There are a lot of other patterns on here. There are patterns such as one known as the hockey stick pattern, where add these 3 and you get that one. Shoot, I did that wrong. But it is here, I promise. Add those 3, get that one. That's kind of where it is. Helps if I pick the right numbers as I go through. There are a lot of different patterns on this. There's a flower pattern that, I'll be honest, I don't exactly remember how it works. There are patterns that other people noticed and they wrote down on their sheet of paper and then they did nothing about telling me about them. Izzy, what did you have written on the side of yours? Do not write this on yours.
Each row, like the sum of it is double for the next row.
Sum of 1, sum of 2, sum of 4, sum of 8, sum of 16, sum of 32, sum of 64. She was trying to figure out how to fill it in. That's what she did. It didn't help fill it in, but it is an important pattern, and actually it's going to be one of the ones we focus on today. So, today we're going to be starting to use our triangle. The triangle can be a useful tool in going through a couple of different things. The triangle is also filled with a lot of patterns, and therefore it's filled with a lot of sequences. Pascal's triangle is a tool that, if you continue on with mathematics, if you go to pre-calculus, if you go to calculus, knowing Pascal's triangle can be hugely helpful. Which is why the first thing I started off with giving you to do was the task of figuring out how to fill it in. Because if you know how to fill it in, you can recreate it, which can be helpful in future classes if that's the path you choose to go on. But that's not actually where the triangle comes from. The triangle is not just built by saying, I'm going to add the 2 numbers above. We could do a lot of different triangles that way. They wouldn't necessarily be mathematically helpful to us. Pascal's triangle was discovered. Wow, I can spell Pascal. It does not have an R in it. Apparently it's going to be one of those days. Did I see it? Done. How the heck did I put an R in Pascal? Twice. Mind you, I legitimately don't know where the R came from. There we go. That's how you spell Pascal. Pascal. Famous mathematician. Also known as Pascal, apparently. Pascal's triangle. The mathematician Pascal was working with combinations. Pascal's triangle is built specifically using combinations. Using a sequence of combinations. So, in my notes, I'm going to write out just a little bit of the triangle, but I'm going to space it out because I'm going to be writing some things that go with it. So, triangle starts with 1, goes 1, 1, goes 1, 2, 1, 1, 3, 3, 1, and I could keep going, but that's going to be far enough for what we need to do. Now, how is it built via combinations? Well, one of the things you need to know about the triangle, and one of the things we're actually going to write on the triangle, is that that first row, that number 1 is actually not row 1. This is actually known as row 0. The next one down is row 1, and then it's counting. Row 2, row 3. So on my triangle itself, I'm going to mark my rows. Row 0, 1, row 2, 3, etc. I've given you the first 15 rows of Pascal's triangle here. Pascal's triangle technically is infinite in size. We just definitely don't need anything beyond row 15. In fact, row 15 might be a little excessive for what we need. Just pausing while people are writing the rows. I'll continue here in a second. Now, the knowledge of the row numbers can be helpful in the sense, one, it's going to be actually one of the main things that you're going to need to know. So it's got multiple uses, but the row numbers are numbered thusly because of how the original triangle was built. It was built off using the combinations. And as it got built off of using combinations, the row number comes from the first number in the combination, the large group that you choose from. So, this is row 0. The number 1 comes off of doing a 0 combination of, and we'll fill the second part in here in a minute. Every number in row 1 comes off of doing a 1 combination of a number. Row 2 is 2 combinations of something. row 3, 3 combinations of something. Now, since combinations are built off of this idea of having a group in which you take a smaller group out of, if the big group has 0 items in it, how many items can you choose out of it? 0. It's your only option. This starts with 0 combinations of 0. If there are 0 items, there is one way that I can choose 0 items. I just don't choose anything because there's nothing to choose. If there is 1 item, how many different options of things could I choose? 1 or 0. This is 1 combination of 0, 1 combination of 1. There are 2 items. I can choose how many of them. Zero, 1, or 2. 2 combinations of 0, 2 combinations of 1, 2 combinations of 2. Seeing the pattern that's happening with the second number? Counting from 0 upwards every time. This is 3 combinations of 0, 3 combinations of 1, 3 combinations of 2, 3 combinations of 3. This is how the triangle was originally built. It became hugely helpful when you have to do repeated combinations, especially in circumstances where you have to do repeated combinations with the same number as the large group that you're choosing from. Because now I know that if I have 15 items to choose from, and I need to figure out how many ways I can choose 0, how many ways I can choose 1, how many ways I can choose 2, I know that it goes 1, and then 15, and then 105, and then 455, and then 1365. I don't have to do the calculation every single time. Which is something that when we get into what we're going to be doing on Monday, you're going to have to do those repeated combinations. And you can either calculate them out by hand. Yikes. Put them into your calculator. Or you can use a triangle that's already got them calculated for you. That's my preference. So, this triangle allows for a little bit of freedom from large calculations and a little bit of freedom from our calculator. So, without a calculator, find. Twelve combinations of 4. $495 with a question mark after it. $220 with a question mark after it. It's one of them. Which one? It is 495. The first number tells you what row to look at. The second number, you'd think tells you how far to go in, except there's one problem. Where do you start in counting? 0. So, have to remember you start counting at 0. means you're looking at the fifth number. 12 combinations of 4 is indeed 495. Seven combinations of 2. What number did you say? That's not what I heard. That's why I was confused. 21? Yeah. Sixteen combinations of 3. You can glare at me all you want. It's not going to change the fact that I asked the question. Now 16 isn't on there, right? But if I look at my triangle, where would be the location of 16 combinations of 0? Here or here? Left or right? Left. So that's combinations of 0. I'm looking for combinations of 3. So that would be 0, 1, 2, 3. How could I find this number? Add the 2 above it. Are you capable of adding without a calculator? If not, we've got a different story to go with. But 105 plus 455, 560. So this is one of the advantages of Pascal's triangle, but to be honest, is it maybe the biggest advantage to do a single combination? Yeah, maybe not. It's good practice to get at, but it's not its biggest advantage, at least in today's day and age where you've got a calculator in your pocket that walks around with you at all times. But there are still other things that come out of Pascal's triangle. And like I said, when you have to do repeated calculations, that's where this really gets its biggest advantage. Now, as I mentioned, there are many important patterns that come with this. Some are more important than others. Each of these important patterns, and there's 3 big ones that we talk about, has its application to something we're going to get into on Monday. But also, it has applications in other fields of mathematics. Pascal's triangle isn't just about going into calculus, it also can help you in going into things that are about statistics and probability. So, first pattern, one of the most important, one of the most basic. The second term in the row, the second number in each row, not the 0, 1, 2. I'm talking like literally you go in, there's a number, there's a second number. I don't care if it's a combination of 1 to get there. That number was already pointed out that row, that diagonal row, counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Now that we have the row numbers on there, do you also notice something else about it? What's the second number in the 15th row? 15. It matches the row number. We're going to talk about why it always matches here shortly when we do a proof. Surprise! Proofs are coming back. They're not like the geometry proofs. These proofs are way easier. I say proof just to give you a jump scare, but I promise you, you're going to see us go through this proof and you're going to be like, wait, that's it? And yes, that's it. Okay. Each row has one more term than the row number. This can be important when you're working with combinations and the idea of, I can say, okay, there's 50 items. I get to choose a group of those items. Size can vary. How many different options for the number of items can I choose? 50 items? I have 51 options. I could choose none, 1, 2, 3, 4, 5, etc., all the way up to 50. This is also going to be really important in situations where you're using the entire list of a combination of a certain number of things. You know you've used them all when you are looking at row 5 and you have 6 items. You're looking at row 12 and you have 13 items. And this one, the one that Izzy found, comes down to the sum of the row. Now, when it was pointed out, when this pattern was initially pointed out, it was pointed out as, well, the sum from one row to the next row just doubles every single time. In other words, multiplies by 2 every time, right? What is repeatedly multiplying by the same number? In a list form, it's geometric, so it created a geometric sequence. But if I say and write 2 times 2 times 2, I can more easily write that as 2 cubed. So what ends up happening, especially since that sum started off as 1, because row 0 adds up to the number 1, it ends up being 2 to some power. Row 0 adds up to 1. Row 1 adds up to 2, 4, 8, 16. It adds up to 2 to the power of the row number. Because 2 to the 0th power is 1. 2 to the first power is 2. 2 to the second power is 4. So it adds up to 2 to the power of n, where n is that row number. That can become hugely helpful because of the fact that Pascal's triangle has a connection to probability. And we're going to talk about that when we get into chapter 11 and how Pascal's triangle and probability are related. What do probabilities always add up to? What percentage? 100%. Every outcome of a probability should add up to 100%. Pascal's triangle always adds up to 2 to the nth power. It can help us essentially see the number of different possible outcomes, and if we're missing any outcomes, because my probabilities, like, they seem to add up to 100%, but do they really? Well, how many different outcomes did I have? 99? There was supposed to be 100. Yeah, I'm missing one. It might be a tiny probability, but I'm missing it and something went wrong. Again, we'll get more into that when we get to chapter 11 and its application, but these are our 3 important patterns that, in the sake of this chapter, we're just going to use them to do a little bit of kind of rote knowledge. And I'll say things like, refer to the 19th row. And I can ask you things like find the first 4 terms of that row. Now you can go to your Pascal's triangle and start adding things up to get to the 19th row if you really want. Do you really want? I don't really want. I'm only to row 15. And while finding 4 terms of the 19th row sounds pretty easy, if I look to go 4 terms in on any row, I need to know a large chunk of numbers that go before it. I couldn't have gotten this 165 without knowing the 45 and the 120. I couldn't have found the 120 without knowing the 36 and the 84, etc. So that becomes a bit tedious when you have to go numerous rows down. So instead, I'm going to do a little bit of calculations. You should always know what the first number of the row is going to be. 1. You should always know what the second number in the row is going to be. 19. You should know how to calculate the others. They're built off of combinations. It's 19 combinations of what? 2. Be careful. Remember, this was 19 combinations of 0, 19 combinations of 1. This is 19 combinations of 2. $171. I want to find the 4th term. 969 because it's 19 combinations of 3. What are the last 3 terms in the row? 171, 19, and 1. Have you noticed that pattern that we hadn't talked about yet? There's always symmetry with combinations. Has to do with the fact that if I had a group, for example here, that's 19 combinations of 2. In all technicality, this would have been 19 combinations of 17. This would have been 19 combinations of 18. This would have been 19 combinations of 19. When it comes to combinations, the way I can choose a group of 2 out of a group of 19 is the same way I can not choose the other 17. There's the same number of ways I can choose 2 versus not choose 17. So that's why the symmetry exists. Same way I can choose a group is the same way I can choose to not choose the rest. How many terms are in the row? 20. 1 more than the row number. What's the sum of the row? Two to the power of 19. Big number. 524,288. So, asking about specific rows is another thing you're going to see. And that's mainly trying to get us into other things that we're going to use with this. There's one other type of problem you're going to see today, and it is a proof. But it's not a geometric proof. You're not going to sit here and write statements and reasons and make 2 columns or to make a flow chart. Proofs outside of geometry often are not two-column proofs or even flow proofs. Proofs outside of geometry are just focused in on this idea of, I know this and I need to justify why. They're going to look a lot more like doing algebra. The only requirement, though, is if it is a proof, you absolutely must show every single step. You skip steps, you're assuming people know things, which is the exact opposite of the purpose of a proof. A proof walks you through exactly why you know what you know. And the proofs will ask you to do things like prove the second term of every row is the row number. If you want to make this proof, you have to go back to what built the Pascal's triangle originally. Not how we built it, what built it. Combinations. You're going to use combinations. Specifically, you're going to use the combinations formula. Remember that formula from yesterday? Yesterday, as we went through it, I said numerous times that there's a reason I was writing out the multiplication rather than jumping directly to a calculator, rather than skipping steps. There was a reason I did it. It's because of how we do our proofs. Doing our proofs requires us writing it all out, because the stuff you're plugging in is not necessarily numbers. So, I want to do this. I want to make this proof. I want to prove that for every row, since I want to prove that it's true for every row, that means the row number needs to stay a variable. It needs to work for every single number I can put in there. So n has to stay in. How far I'm going in, though, for every single one is the second term. And every single one, the second term, is some combination of what number? 1. The second term in the row is always some combination of 1, which means we're looking at doing n combinations of 1. Now I'm just going to write a little note to myself, because this is a notes and I want you guys to be able to figure out where this came from. N stays n, because it has to work for all rows. And r is equal to 1, because all second terms are some n combinations of 1. When it says prove that the second term of every row is equal to the number 1, it's asking us to prove n combinations of 1 is equal to the row number is n. That's what this prove is asking us to do. Have a wonderful day. See you later. Well, how do we prove it? We have a formula. We're going to plug things into the formula, and we're going to simplify them down as best as we can in order to get down to where it simplifies to n. That's what these proofs are. is literally plug in what you know and simplify. We are looking for n combinations of 1 equals. I'm plugging into this formula that says n combinations of r. N stayed n, which means n factorial is still n factorial. Over. N minus r in parentheses factorial does change because r became a 1. So it becomes n minus 1 factorial. R factorial is 1 factorial. There's step 1. Plug in what you know. Step 2, start simplifying. Are there any of these 3 factorials that's really easy to simplify right off the bat? What's 1 factorial? So that means we've got n factorial over, in parentheses, n minus 1 factorial. Yes, I could write times 1, but I am going to assume that you and anyone reading this proof is at the level to understand that when you multiply by 1, it doesn't do anything. So, that's simplified out. Now I need to simplify this. Again, yesterday I explicitly wrote out, as we went through, when I had 30 factorial, I wrote 30 times 29 times 28 times 27 times 26. And when in the bottom I had 28 factorial, I wrote 28 times 27 times 26 times 25 times 24. I did that for a reason. That's what we are about to do. N factorial is n getting multiplied by. What's the next number smaller than n? N minus 1. To get to the next smaller number, you subtract 1. N minus 1. What's the next smaller number? N minus 2. What's the next smaller number? N minus 3. Now, I don't know what n is, so I could go on forever. So times, dot, dot, dot. Though the one thing I should do in these proofs is I should also write where do I stop. Where do I stop multiplying in a factorial? The last number? Not 0. If you multiply by 0, you get 0. 1. 5 factorials, 5 times 4 times 3 times 2 times 1. You stop at 1. 7 factorials, 7, 6, 5, 4, 3, 2, 1. Okay, so I'm also going to put that I'm going to stop at the number 1. Over. Denominator is n minus 1 factorial, which means I multiply by n minus 1 and every number smaller than it. So I start with n minus 1. What's the next smaller number? N minus 2. Next smaller number? N minus 3. Could I keep going? When do I stop? 1. What's going to happen? Yes?
How do you get to 1 if your numbers are getting bigger?
And where did the n?
Why are they getting bigger?
Because you're going 1, 2, 3. Well, they're getting smaller.
But I'm not going 1, 2, 3. I'm going 3, 2, 1. Not in a proof. It's a proof, you gotta write it out. Now, if you wanted to do n times n minus 1 times and then do the dot, dot, dot to 1, I wouldn't hold it against you. So if you didn't want to write these two, I wouldn't hold it against you, but. Isn't some stuff gonna cancel out? Gone, 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 gone. It's the only thing that's not gone. N. That's the proof. That's the entire proof. because by asking us to prove that the second term of every row is the row number, I already established we're trying to prove that n combinations of 1 is equal to n. So we did n combinations of 1. We plugged it into the formula. We simplified, we ended up with n, which is where we wanted to end up. That's the proof. There are 4 common proofs that come with Pascal's triangle. They all look like this. I gave you one of the 4. 2 of them are on your homework. The third one will come up.